welcome to the channel Physics by IITians. Today we learn about vibrational spectroscopy or infrared spectroscopy. We will learn about the vibration of a molecule. We will learn about the harmonic nature of vibration. We will learn about anharmonicity and all the consequences of vibrational spectroscopy. So I request you to watch the full video to get all the physical pictures of vibrational spectroscopy. So let's start the video. So vibrational spectroscopy or the infrared spectroscopy. The name, you can understand that the spectroscopy which is arising due to the vibration of the molecules. Okay, so it is also infrared active because the vibration gives you the spectrum within the range of infrared radiation. So when we will get infrared active molecules or vibrational spectrum, when there is a change in the dipole moment. Okay, because oscillating dipole moment can generate radiation and electromagnetic radiation. So the infrared active molecules can have permanent dipole moment, and this vibration of the dipole can lead to the generation of electromagnetic radiation in the form of IR radiation. Okay, so heterogeneous molecules have permanent dipole moment like HCl, like NaCl. They all have permanent dipole moments. Okay, now there may be induced dipole moment. What is induced dipole moment? Because there will be oscillation, okay, oscillation of the atoms, and due to that oscillation can induce some dipole moment, and due to this change in the dipole moment, this oscillation of the dipole moment, it can give infrared radiation also, and the molecule can be infrared active like CO2. Here in case of it is a linear molecule, and here no net dipole moment or net dipole moment is zero. There is no permanent dipole moment, but while it is stretching, okay, while it is vibrating in a certain way, it has induced dipole moment, and that dipole moment will lead to the generation of IR radiation. We shall first understand what is molecular vibration, what are its modes, then we understand it more deeply. Okay, so first we should know what is molecular vibration. A molecule has translation and rotational motion as a whole, while each atom has its own motion. The vibrational modes can be IR or Raman active. Today we are focusing on IR active modes or IR spectroscopy. The normal modes of vibration are symmetric, asymmetric, wagging, twisting, scissoring, rocking for the polyatomic molecules. Now we will understand what are the stretching, what is the bending or deformation. Like stretching, what is symmetric stretching? Symmetric stretching means, suppose this is a molecule, okay, diatomic molecule. So these atoms are stretching like this way. This is called symmetric stretching, okay, or this is like this way, or this is asymmetric stretching, where this is the uh, stretching, or this is the extension, and this is the compression. This is asymmetric stretching, and this is both the extension of the internuclear bond length is happening here, okay, or both here. This is the symmetric stretching, this is antisymmetric stretching. Okay, what is bending or deformation? Like scissoring. Okay, so you have to understand this is a scissoring motion of the molecules, in motion of the atoms inside the molecules. This is the twisting. This is plus or minus sign, means plus is the out of I mean, if you consider this is a plane, okay, the screen is your plane, the atoms is coming out of the screen, that is the plus motion, and the atoms which are going inside the skin, that is minus. Okay, so one is coming up, one atom is going down. So these are different vibration motions of any polyatomic molecules. These different vibration motions can give you different radiation in terms of IR radiation. Now we should understand how the CO2 molecule can be IR active when it has symmetric vibration. Okay, this is, suppose this is our CO2 atom. Okay, symmetric vibration means both are here compressed. So both the this is R, and suppose this is the internuclear distance between this O and C, and this is the internuclear distance between this O and C. So since the bond length in both the cases are compressed, there is no net dipole moment. Suppose, or since both the R or internuclear distance or bond length is extended, so there is extended with the same amount, compression with the same amount, extension with the same amount, so we get no net dipole moment. Okay, but if suppose this compression and extension is not with equal amount, if there is symmetric stretch, asymmetric stretching, what will happen? Suppose this is O, this is C, and this is another O. This is along this direction, this is along this direction. So this time this distance is smaller than this distance, because here it is compression and here it is extension, so that we can get a net dipole moment, and this is an induced dipole moment. And that's why, due to the change in the induced dipole moment, or due to the vibration of the induced dipole moment, we can get IR radiation. So the symmetric vibration is not IR active, but the asymmetric vibration is IR active. Or suppose we are considering the bending of CO2. So it is, suppose the CO2 is bending like this way, and at some another instant it is coming to its back its position, then it is going like this way. So there are continuous changing of the dipole moment or oscillation of the dipole moment. So the induced dipole moment is not zero, so IR active. So we have already learned about rotational spectroscopy. So rotational spectra is microwave active, and it has rotational spectra we can only observe where the molecules have permanent dipole moment. But vibrational spectra, we are learning that it is IR active, and molecules can have permanent dipole moment as well as they can have induced dipole moment. That is the basic difference between the rotational spectra and a rotational active molecule and a vibrational active molecule, or IR active molecule and microwave active molecule. Okay, so here we are already told you, I already told you that suppose we are taking CO2. Okay, so the symmetric stretch, look here carefully, symmetric stretch, both the bonds are stretching, so here we get no induced dipole moment. When we are considering antisymmetric stretch or asymmetric stretch, one bond length is lower, compressing, another bond length is extending. So the difference is here, you can see. So due to this difference in the bond length, we can get an induced dipole moment. Also in case of distortion or bending, you will get induced dipole moment. So these two modes are IR active here. Okay. Now we'll learn about some energies, vibrational energy of the molecule. First we have to understand where does these energies come from. In case of molecule, we are taking the diatomic molecule for the simplest case. When the two atoms are forming a molecule, there will be coming two forces. One is the repulsive force and another is the attractive force. Repulsive force between the similar charges, Coulombic repulsion, and attractive force between the dissimilar charges or opposite charges, that is Coulombic attraction. So now at equilibrium, the total force will be equal. So if you plot the bond length versus the potential energy versus bond length, okay, how do the what will be the nature of the diagram? What will be the nature of the potential energy versus internuclear distance between two atom diagram? Here look, this is potential energy, this is attraction and repulsion, and this is the bond length, internuclear distance. So the internuclear distance at some equilibrium point where the attraction equals to the total energy of the attraction will be the energy for the repulsion, that will be the internuclear separation or the equilibrium distance. Here look, this is the force between the nucleons we are plotting along y direction suppose, and this is nuclear separation. So the electrostatic force is playing the role here. So the typical nuclear separation is the equilibrium separation where both forces are balancing each other. Okay. Now if we look this for this much region where delta R is very lower, we can write the force is as simple harmonic oscillation. Look here, the nature is quite simple harmonic. Although this is not correct, but we can think that the atoms are vibrating inside the molecules, so we can assume it the vibration is a linear vibration is happening as a linear harmonic oscillator, and we can think it atoms as of spring mass system. Okay, so suppose M1 and M2, the two atoms, and we are considering the vibration is happening as a linear harmonic oscillator. So we can plot the energy for the linear harmonic oscillator with the internuclear separation, or simple harmonic oscillator with the linear internuclear separation this way. What will be the energy or vibrational energy? So quantum mechanically we can get the simple harmonic oscillator energy is V plus half h cross omega, where V is the vibrational quantum number. Okay. Now we shall understand what should be the energy levels of the different vibrational energy levels. So for here in this diagram, what we have learned as V, here it is written as N. So En equals to N plus half h cross omega. Now for N equals to 0, we get the ground state energy, ground state vibrational energy. N equals to 1, N equals to 2, N equals to 3, N equals to 4. We can get different vibrational energy levels. And the transition allowed is between N equals to 0 to N equals to 1 or N equals to 1 to N equals to 2. So we here assume that the vibration is simple harmonic oscillator. Look here, the two atoms are oscillating like a spring mass system. Okay. So the omega naught will be k root over k by mu, where mu is the reduced mass. Nu naught is 1 by 2 pi root over k by mu. Omega naught bar equals to, that is in terms of the wave number, we can write it as 1 by 2 pi c root over k by mu centimeter inverse. So the vibrational energy levels in terms of wave number, we get EV by Hc, that is V plus half omega naught bar, where V equals to 0, 1, 2, 3. Now we put the value for V equals to 0, we get E, that is wave number for E V equals to 0 is omega naught bar by 2, V equals to 1 equals to omega naught bar 3 by 2, for V equals to 2 omega naught bar 5 by 2. So what will be the wavelength separation, that is delta E, will be, suppose we are taking the transition between V equals to 1 to V equals to 0 level, we should get a wave number of omega naught. Okay. For the suppose we are taking the transition between V equals to 1 to V equals to 2, we also get omega naught bar. We are taking the transition between V equals to 2 to V equals to 3, we will also get omega naught bar, because the selection rule is plus minus 1. So we should get only a single spectral line having a single wavelength or a single frequency and or single wave number, that is omega naught bar. But what observation tells us, that observation tells there are also other lines accompanying this single line. So our assumption that vibration is simple harmonic, that is not correct, and the vibration is actually not simple harmonic. What should we have to understand here? The simple harmonic oscillator, what we are thinking of the about the model of oscillation or vibration is not correct. What should we think? We should know about the anharmonic oscillator. And where does this asymmetry come from? Why is the anharmonic oscillator? Anharmonic means which is not harmonic. So we have to understand where does this asymmetry come from. So in real pictures, energy changes are not same amount for the same amount of compression and expansion. Suppose you are taking this. Suppose this is our diatomic molecule. This is the energy, okay, versus R plot. R is the internuclear separation. So whenever this is the equilibrium separation R naught, suppose bond is stretching or bond is compressing. For the stretching, suppose we are taking this side, the stretching side. So R naught is delta R naught. Suppose due to the stretching there is change in bond length, or due to the compression also there will be change in bond length, that is delta R naught. I am telling you the change. So the change in the compression is much more steeper than the change in extension. So the change in the compression, earlier we were taking the linear harmonic oscillator, where this is the delta R, that is the internuclear separation, where the change in whether it is due to the compression, whether due to the extension, both the cases change was same. But in the real case, or in the real molecule, we have to consider there is the change is asymmetric, or change is not the same amount when we calculate it for the compression and when we calculate it for the extension of the molecule. So for the compression there is a sharp change in energy, for the extension there is a slow change of energy, and this is coming from this kind of potential, and this kind of potential is known as anharmonic potential, or this kind of model is known as anharmonic oscillator, where what is the potential energy for this anharmonic oscillator? P.M. Morse, he calculated the empirical formula, that is experimental form. He calculated the formula which fits with the experimental curve, and he gave the formula for the energy, potential energy for the anharmonic oscillator as E equals to dE into 1 minus exponential of minus beta to r minus r naught whole square. This is also known as Morse function, where dE is the dissociation energy. What is dissociation energy? Dissociation energy is that energy when the internuclear distance is that much that the atoms can be separate out. Okay, this is known as dissociation energy. Here, look here, we are taking the anharmonic oscillator, where suppose this is the internuclear distance for the equilibrium distance, for the equilibrium case, equilibrium internuclear separation. So due to the, here it was earlier harmonic oscillator with assumption is given as green line, and the anharmonic assumption with the blue line. Look here, the change delta r in this case and change delta r in this case are different. They are not symmetric, where in earlier case change in delta r along this side and change in delta r along this side was same or same. Okay, that's why we get the anharmonic oscillator or anharmonicity. What should be the energy of the anharmonic oscillator? We should solve the Schrodinger equation and we get that energy in terms of wave number. I am telling you that EV equals to V plus half omega E bar minus XC into V plus half whole square omega E bar, where X is the anharmonicity constant and it is related to the dissociation energy, that is omega E bar divided by 4dE, where dE is the dissociation energy. Now for the simple harmonic oscillator case, we had EV equals to omega naught bar into V plus half, and now the anharmonic oscillator case we get EV equals to omega E bar into 1 minus XC V plus half into V plus half. So omega naught bar equals to omega E bar into 1 minus XC to V plus half. So anharmonic oscillator can be assumed to be harmonic or simple harmonic oscillator with a different frequency, with a modified frequency of this amount. So you have to plot the potential energy for the anharmonic oscillator, and for different V values, that is for different vibrational levels, you are plotting as for V equals to 0, 1, 2, 3, they are all with decreasing order, because here for V equals to 0, it will be half XC, 1 minus half XC. For V equals to 1, it will be 1 minus 3 by 2 XC. For V equals to 2, it will be 1 minus 5 by 2 XC. So the separation will be of decreasing order due to this anharmonicity factor. What will be the selection rule? For the earlier case, selection rule was delta V equals to plus minus 1. For the anharmonic case, we have to consider not only plus minus 1, but also we have to consider delta V equals to plus minus 1, plus minus 2, plus minus 3, etc. What will be the change? That is delta E, change in the wave number, or what will be the transition? That is delta E equals to, for E equals to V equals EV equals to 1, 2, 3 level to EV equals to 0 level. Now we will define some definitions, like from V equals to 0 to V equals to 1, we tell it the fundamental band. From V equals to 0 to V equals to 2, we tell it first overtone band. From V equals to 0 level to V equals to 3, we tell it second overtone. What will be the change in energy, or what should be the wave number? So first we should calculate it. How do you calculate? Suppose we are calculating for the first fundamental band, that is V equals to 0 to V equals to 1. So we have all this formula, that EV equals to V plus half omega E bar minus X into V plus half whole square omega E bar. So for V equals to 0, you put this formula V equals to 0. We get E V equals to 0 equals to, that is half omega E bar minus 1 by 4 XC omega E bar. For E V equals to 1, we get 3 by 2 omega E bar minus 9 by 4 XC omega E bar. So delta E will become the difference between the two levels, that we get as omega E bar minus 2 omega E XC bar. So this is the wave number of V equals to 0 to V equals to 1 level. Similarly, for the first overtone, we should calculate from V equals to 0 to V equals to 2 to V equals to 0 difference, and for second overtone, we should calculate the wave number difference for V equals to 3 to V equals to 0 level. Okay. So what will we get? We get as V equals to 0 to V equals to E, delta E as omega E bar into 1 minus 2 XC. For V equals to 0 to V equals to 2, delta E equals to 2 omega E bar 1 minus 3 XC. V equals to 0 to V equals to 3, delta E equals to 3 omega E bar 1 minus 4 XC. These are all given in any standard textbook, what you have to understand the physics here, why these all are happening, why this harmonic oscillator model failed, and we have to include the anharmonicity term. That is important. So we should get here the not a single line with omega e bar wave number, but also some other lines, and these lines will be of decreasing order. Separation will be of decreasing order due to the anharmonicity. So for the harmonic case, we should get just one single frequency. Now we get several different frequencies. So why we are considering v equals to 0 to v equals to 1 state, or v equals to 0 to v equals to 2 state, or v equals to 0 to v equals to 3 state? Why we are not considering the other vibrational state or higher vibrational state? So because we are calculating this at room temperature. Now at room temperature, we find out that the population of the molecules, that is, suppose we are taking the vibrational level for 1, the number of population of the molecules is n1, and at vibrational level v equals to 0, then the population of molecules is n0. The ratio between n1 and n0 is 0.008. So the population at v equals to 1 level is very low, and that is less than 1% at room temperature. So at room temperature, most of the molecules are at ground state, that is v equals to 0. So that's why we are considering this vibrations, that is we are considering from v equals to 0 level to v equals to 1, 2 or 3 levels. Now if we increase the temperature, we will definitely get vibrations from v equals to 1 level, v equals to 2 levels. So from v equals to 1 to 2 level, this is called first hot band. From v equals to 2 to 3 level, we call it second hot band. Why these are called hot bands? Because it requires much more temperature. So that's why these are called hot bands. What will be the wave number difference? That is delta. For the first hot band, it is omega e bar 1 minus 4xe. For the second hot band, it is delta e equals to omega e bar 1 minus 6xe. Okay. Now we should understand now how these vibrational bands are, why we are calling it bands, or how the vibrational spectrum we are what should be, how the diagram, or how to draw this vibrational spectrum, or what will be the nature of the vibrational spectrum, we should understand. So we are not getting a single frequency lines, we are getting several lines, and these lines are not coming from only vibration. Also we have to consider the rotation of the molecules, and we all know that within one vibration levels, this is another CO. Look here, this is CO2 vibrational spectrum, carbon dioxide, and this is the vibrational spectrum for HCN, hydrogen cyanide. So why we are getting these branches, R branch, P branch, what are these? We have to understand it. These are coming due to the rotations also. So the within a one vibration, there are several rotational energy levels. So due to these rotational energy levels, we have rotation spectra, and the rotation spectra, that is, suppose we are taking v equals to 0 to v equals to 1 level. Okay, and within v equals to 0 level, there are several rotational states like j equals to 1, 2, 3, 4. These are the j value, that is the value representing the rotational energy levels, and this is also the second for v equals to vibrational level 1, we get several rotational energy levels for 0, 1, 2, 3, 4. Within these rotational energy levels, there will be certain rotational transition, like from 1 to this one. Look here, this is 1 level and this is 0 level. Okay, so the rotation delta j equals to plus minus 1. So you have to consider the different transitions of the rotation, different rotation levels. So that's why we get this bands of P or R. When delta P we get when rotation is minus 1, that is delta j equals to minus 1, we call it P branch. Where delta j is plus 1, we call it R branch. Okay, look here this P branch, R branch. Okay, so these are happening due to the inter-rotational energy level transition inside a vibrational levels. For that's why we are call it a band, not a spectrum. I think you understand the physical picture of vibrational spectroscopy. If you find this video helpful, don't forget to like this video. Don't forget to share with your friends. If you find our efforts is helpful for you, you can help us by clicking the link given in the description box. Thank you.